Yeah, hello together to our course in statistics, and the next topic in our lecture is the so-called linear regression. And at first we just want to start, and this I think all of you know already, is yeah, to represent this topic, and that we represent data within a scatter plot. And what we have here is just that we have two variables. You can think of that this is some enterprise, and here in the second line what we have is the number of orders, and in the third line we have the amount of euros. What are these orders are worth altogether. And here then you see, for example, this guy made two orders worth 36 euros, and this is much more on average than, for example, this guy number 5 with two orders and only a volume of 21 euros. And yeah, what we want to do is to have some idea how these two variables, order and volume, are if they are independent or if they depend on each other. So question: what is the dependence between the two variables, order and volume, measured in euros? And for this we represent these two variables in a scatter plot. Though, for example, on the vertical axis we could put volume, and on the horizontal axis, for example, order. And this, of course, we will do, and this, of course, again, we can do in Excel. And where is my this one? This. So then we put the data in our table. And let's see how these two variables look like. Copy. Or let's, of course, put it in another way. So we transpose this data. And we can see it in a better way. So, and then, of course, we mark this data, and this is here the possibility to show this data in a scatter plot. This is too large. You can see it. Let's do it like this. And yeah. So, which one is X and Y? Then we see A order is on the vertical axis and B is on the horizontal axis. This is okay. And so we have order and volume. Well, and this is always a good thing to do, that at first, if you have data, that you use some graphical representation. So let's put this into our slides. So, and what kind of assumption would we make if we just have a look at this data? So what kind of dependence do we have if we just look at the data? So what we are doing is that we make about these dependence some hypothesis. So what kind of hypothesis can we make? What would you assume? If you have a look at this plot, what kind of assumption could you make? Any idea? So if you go here from left to right in order, so order increase, what happens then on average if you look at this plot for the variable volume? Yes, great. This is a simple, but this is then the hypothesis which we will make, and then after we have this hypothesis, then we will start to quantitatively analyze this data. So hypothesis, the higher the number of orders, the larger is, oops, the volume. So, and what we then quite often do is that we just fit by eye something like a line into the data in order to represent this hypothesis which we made. And what is a linear regression about is just linear regression. How do we have to fit a line in order to represent our hypothesis? Okay, of course, it would be not a good idea to do this just by hand. And how we developed this method, this is what we want to talk about now. So then let's go to another example where we do not have that much data. And yeah, there maybe we can say we have another company and we want again know how is the dependence between our sales volume and the visits of our representatives. And yeah, then the question could be, should be hire some more representatives because we just want to know if we increase our number of visits, that it would be much larger than the data we have. So x equals 30 is, oh, this you don't see, sorry. Much larger than the data we have. So this is then something similar as we made our forecasts. So we want to have an idea what could be our sales volume if we significantly increase the number of our visits. And this is a reasonable question in a company because then maybe we need to hire new people. And of course, then we have to pay these people. So we have to have an idea where would be our sales volume if we increase our number to, for example, x equals 30. Let's plot also this data. Now this is just a picture, so I have to type the data. X and Y. 9, 11, 5, 13, 20, 12. 9, 11, 5, 13, 20, and 12. And we have 24, 33, 24, 33, 10, 29, 42, and 24. So volume and visits. Again. And let's increase our horizontal axis to 30. And this also. Or even more. And if we now make, for example, by eye and fit, then we could think that maybe we have a line lying here, and what we are interested in is this possible point up here. So let's also take this data. Oh. And copy into my drawing. So we are interested in the possible value of volume if we increase the number of visits up to 30. So this is visits, and this would be volume. And again, of course, we are interested how to fit in a good manner this line, which should represent again the dependence, that the more we the higher the visits, the higher the volume. Okay, so what we want to do in general is that via a linear regression, and this means that we want to fit here a line how to fit a linear line. And then, of course, we distinguish here on the vertical axis between our dependent variable y and our independent variable x. And so to speak, we want to explain our variable y with this variable x, and it then just means that we want to have an idea what means a change of x for the variable y. Oops, this is still a journal. And what we do is that we want to have an idea which kind of linear function, for example 3 plus 2x, shall we use if we have our data, or of course in general y equals x a plus bx. And so this is the point on the vertical axis, and this is the slope of the linear line. And well, let's have a look at some data. So graphically, in this case, it would be quite easy because all the data points lie already on a linear line, and in this case, of course, then we have here 1 to the right and 3 to the left. So for the blue line, which kind of linear function represent the data, and also for the red function here, you see I go 2 steps to the right and then I go 1 step on the y-axis downwards. So what would be for the red data points and for the blue data points our linear function? So let's start with the blue one. So what we look for is y equals a plus bx, and we want to know what is a and b for the blue data points. So here we have 1 and this is 3. Any idea? So first of all, I think what we can already directly see it, what is the slope of our linear line for the blue data points. Yes, A would be 2. Yes, I think so too, because here we would go 3 downwards, 1 to the left, and 3 downwards, and 1 to the left. Great. So here we have then y equals 2 plus 3x, and let's also do it for the red. And ya plus bx, a and b. So here we have 1, and this is 2. So what would be a and b? Yes. So again, 2 to the left and 1 upwards, and then we are here. So we would have y equals 20, and then you said 1/2. I need also an additional information. Minus, of course. Yes. So because here we have anti-proportional dependence, and in this case we have a proportional dependence. So this would be proportional. This means the higher x, the higher is y, and in the red case we have an anti-proportional dependence. And this of course means the higher x, the less is y. Okay, and then let's step again to our example we already had with our cells volume and our visits. This we have already done here, where we made just a fit by eye, so to speak. We could then again think of that we maybe would have maybe a line looking like this, and this could be that maybe we start here at 1 and going to the right, and maybe then we go up here to 12 supposed to be, and then it would be that a fit by I for example would be y equals 1 plus 11 over 5 times x. But of course, now we want to talk not to do it by I, but to do it in a quantitative manner. So what we are looking for it, or what is the question, but what would be a good, so to speak, line, or what is the best linear function we can fit. And for this, we construct an optimization problem. So the question is, how shall we calculate these regression? And yeah, if we look here at our data, then of course, only in this special case here, we have the case that all data points are already lying on our fitted line. In general, of course, we always would have data where in general the data points would not directly lie on our line. So what we can then construct is that we have our data points yi and xi, and that we then calculate hypothetical points which correspond to our true data points. So what I draw here is the distance between our hypothetical point. Oh, on this point you don't see this. So this is our, oops, hypothetical point, and this is the true data point. So what we make if we draw our line is some slight error. So this is then the difference between our true data point and our hypothetical data point. Well, and what is linear regression about is that we sum up all these distances and that we then start to minimize the sum of these squared distances. Well, and then we can ask, why is it a good idea to use the sum of the squared distances? So why do we use the squared distances? Well, at first, of course, we can say that we use not only the distance. This is quite clear, because here, if our data point is above our linear regression line, then the distance is positive, and if this data point lies below our regression line, the distance would be negative. So, first of all, we want to have a measure which does not distinguish between a positive and negative distance. But then the question is, we can get rid of this problem also if we just use the function of the absolute value, y hat I minus yi. Then we would also get rid of this problem here. Do you have any idea why we don't use this absolute value? Well, how does this function looks like, the absolute value function? If we draw this function in a diagram, then this function would look like this. And so this function has one property which we do not like, so to speak, and this is that in the origin there we have this kink, and this means in this origin we have no derivative. So here no derivative exists. So this is then a reason why we just use here the squared value. Oh, this one. Because also with the squaring we also get rid of the problem of the plus and the minus signs. So then this would be the second reason, with the squared value of the distance we have a function where the derivative exists. Well, and then of course we already know this kind of squared distances from statistics. So what is also these sum of squared distances of data points? Where do we also use squared distances? Which kind of variable in statistics is also defined as squared distances? This we had also in this lecture. So remember, this was sum of xi minus x bar squared 1 over n. What is this for a variable in statistics? So the sum of the squared distances with respect to the average of the data. So what is this here? X bar is the average, and the squared distances are well, this is of course our variance. So what we define here is highly connected to the concept of variance. Well, and then my question, maybe you have heard about this in other statistics lectures. Well, why do we use explicitly here the squared? All of this we could also get by, for example, the kurtosis we talked about. Why do we use this square so often in statistics? Well, if you think of the density function, f of x equals 1 over square root of 2 pi e to minus sigma e to minus x bar squared over sigma. This density function you hopefully have already seen in other courses. Which distribution represents this density function? And here, of course, we see that we have our variance. Well, this is the density function of the normal distribution. And there we can say that since the normal distribution has such a high relevance if we are doing statistics, and we know if from the central limit theorem that we increase the number of our data points, that we then will move approximately to the distribution, to the normal distribution. And since we can represent the normal distribution via the variance, then it is also a good idea to use these square distances if we want to look for a so-called best fit of our data via a linear regression. So since the squared distance is directly connected to the representation of the normal distribution, we can say that minimizing the squared distances is oops, the best, so to speak, fit. Well, I think in the most lectures we just say, well, let's minimize the square distances, and this is the linear regression. But I think that we should also think about the question, why is it a good idea to use these square distances as our optimizing function? Well, and so since we motivated here with these 4 points that it is a good idea, then let's do it. So what we then do, this is just always our error squared, and then we can say this is all our data points. These are the known data points. And then, of course, we have here only the point on the vertical axis and the slope as our variables. So these are variables. And this means that we now have a function of these two variables. And then we want to find the numbers for A and B such that this sum is minimized. And what do we have then formally to do? If we want to minimize a function. Or think of a one-dimensional function, f of x, and this we want to minimize. What do you do then, formally in mathematics? Or the other way around, if you want to maximize f of x, what do you do then? Think of the case f of x equals px minus c of x. This is nothing else than profits. What do you do then if you want to maximize profits? Yes, great. We just take the first derivative, and if we have a two-dimensional function, then of course we have to calculate both derivatives, once with respect to a and once with respect to b. So this means we have to calculate the f with respect to a setting to 0 and the f with respect to b has to be set to 0. So what we then need is, what is the f with respect to a? Well, this looks maybe a bit complicated, but if you just think of how does this sum look like, then this is y1 minus a plus b x1 plus y2 minus a plus b x2 plus yn minus a plus b xn, and all this of course squared. So what is then the derivative with respect to a? So if we take maybe this one, because I think you also see that it is always the same thing which we have to do. So if we know the derivative of this part here, then we know that the total derivative is just the sum of these. So what is the derivative of this function? which kind of rules for derivatives you have to use. Or let's make it explicit that y1 should be 2 and, for example, x1 should be 3. And then we have 2 minus a plus 3b in brackets squared. This is a function of f of a. What is then f prime of a? No idea? So if you have f of x is x squared, what is f prime? Nobody? Well, in this case, we have 2x. So we have to calculate the outer derivative. This is 2 times 2 minus a plus 3b. And then, of course, we have to calculate the inner derivative. So if you think of your function g of a would be 2 minus a plus 3b. What is then g prime of a? So in this case, it is just minus 1. So what we obtain then with the derivative with respect to a is the sum of yi minus a plus bxi in brackets and a minus sign in front from the inner derivative and all this times 2 from the outer derivative. And this has to be 0. And the second derivative with respect to b, then of course we have the same outer derivative here. And now let's say that h of b is 2 minus a plus 3b. And then we have h prime of b equals minus 3b. And remember that this 3 is just an example for some possible xi. So our inner derivative is then xi. So what we then obtain is again minus the sum of yi minus a plus b xi, oops, times xi and also times 2 equals to 0. And what we then have here is a two-dimensional system in two variables, and this has to be solved for a and b. And this I gave you also on the next slide. So this is our two-dimensional system which we can directly solve. Sorry. And if we solve this problem here, then, well, this looks a bit complicated. This we don't want to do then right now. And we obtain then these formulas here for A and B. And the nice thing is also that we can show that A is just equal to the average of our data points for the data of the dependent variable minus the slope of times the average of the data point for the independent variable. So if we have calculated B, then we can put in this into these two average points and we obtain directly A. So this means also that the average data points lie or are lying on the regression line. And also what we can say is that B is directly connected, of course, here again to our variance and the so-called covariance. And the variance is then the covariance is then just the interpretation of a variance if you have a multidimensional system. So you can then, of course, say that the variance of x is nothing else than the general covariance of x and x, because then we could write 1 over n the sum of xi minus x bar times xi minus x bar, and this is nothing else than xi minus x bar squared. So what we have done then is to wait, since my computer has to save. Is that if we go back to our example, that what we have done is just we all summed up all these little squares, and that then we minimized, so to speak, the sum of these squares. Saving quite a long time, sorry. So, and what we see here is just that we need the sum of our variables, that we need the product of our variables, and we need also the square of xi. And so we will just do this regression for our example. Then let's take this data again. Put it in here. As you can see, yeah, oops. And what we need then is that we multiply this 9 times 24. Oops. And we need x bar squared or x squared. This would be this number squared. And if we look in our formulas, where are my formulas? Here. Then we always need just the sum of these numbers. So we need the sum of xi, the sum of yi, we need the sum of xi squared, and afterwards also we need the sum of xi and with the outer brackets squared. So then we need always the sum. And then we can calculate b equals n times the product of both data points, or let's put it in here. So if we have the sums, then we have 17, 70, 160. 62, and let's put this in here. Oops, that is too much. Why doesn't this work? So, oops, 16. What is missing? So 8, 9, 10, 11, 12, 13. 8, 9, 10, 11, 12, 13. But 260, 81, 50, 25, 840, 400. Oh, this one is missing. 288 and 144. So 2000, oops, 2134 and 940. And we have n is 6 data points, n equals 6. So let's go to our formula. Then we have 6 times the product, 6 times the product, 2134, minus the product of the sums of the values x and y, minus 70 times 162 divided by n times x squared, six times x squared 940 minus the sum of x and this number squared. So the sum of x is 70 squared, and this will be then, let's calculate this here. So this is then 6 times minus x squared times y squared divided by 6 times x squared minus sum of x squared, and then I also need here some brackets. And a, and there we have this nice formula here, that we have y bar minus bx bar. So y bar minus bx bar, and y bar is of course 70 over 6, x bar, and y bar is 162 over 6. So we obtain then, this was 0.97, I think, 98 roughly, and this is then 70 over 6 minus 1.98 times 162 over 6, and let's calculate. This one is 70 over 6, no, y, this is 162 over 6 minus b times 70 over 6, and then we have 3.910. Oh, sorry, this was wrong. Nope. 162 and 70, and this is 3.92. Well, of course, in our software package, we have also the possibility to calculate this directly, and this would be then here the function slope of these numbers up and these numbers up. Oh, here we have to use a semicolon, and this is the axis point, so we have directly this possibility. But I think it's a good idea that you once have seen where does these values really come from, that you actually know what you are doing if you are doing a linear regression. Okay, that it was for today. Thank you very much.